Hello students, in previous lecture we discussed what is meant by the chelating agent, chelate, chelation and chelate effect. In continuation with these terms, in this lecture we are going to discuss the characteristics of metal chelate. So let's discuss the characteristics of metal chelate. Characteristics of metal chelate. As we know that the metal chelate are more stable than the simple complex molecule. So generally in metal chelate, 5 or 6 member heterocyclic ring are formed. Metal chelate, in metal chelate generally ligand is a chelating agent, so it can form a ring with the central metal atom. So that's why generally the 5 member or 6 member heterocyclic rings are formed in metal chelate. Metal chelate are more stable than the metal complex. Metal chelates are more stable than metal complex because due to chelation, entropy of the complex increases, so that's why the stability is increases. Now the third point, metal having high charge have a high tendency to form metal chelate. High charge means there is a high tendency to donate. So that's why if there is a more donation, there is a more tendency to form metal chelate. Fourth, in metal chelate, coordinate or covalent bond is formed in metal chelate. So these are the general characteristics of metal chelate. Now let's discuss what is meant by the metal ligand ratio. Metal ligand ratio is nothing but the ratio of total number of metal ion to the number of ligand is known as metal ligand ratio. And the example of this metal ligand ratio, that is, if we take an example of platinum complex, that is platinum diammonium dichloroplatinum complex. In that, platinum is only one metal, so the only one atom of metal, that is a platinum, and the number of ligand, how many number of ligand is here? There are total 4 ligand, 2 ligand of ammonia and 2 ligands of chlorine. So total 4 ligands are present, so the 4 atoms of ligand are present, so the ratio for this complex is a 1:4. In second example, that is in cobalt complex, that is a penta ammonium chlorocobalt complex. Here again the number of metal ion, that is 1, and the total number of ligand here is a 6. 5 molecules of ammonia plus 1 molecule of chlorine. So the total number of ligand is a 6. Don't confuse with this Cl2. It is a counter ion. It can balances the charge of the complex. So just here 6 ligand. So the ratio, that is a 1:6. From this metal ligand ratio, we can easily calculate the coordination number of the metal complex, then geometry of the complex, and the reactivity of the complex. Now let's discuss the difference or the comparison between the metal chelate and metal complex. So let's discuss the comparison between the metal chelate and metal complex. As we know that in metal chelates are generally formed by multi-dentate ligand. Multi-dentate ligand is having 2 or more than 2 donor sites, whereas metal complexes are formed by simple monodentate ligand. There is only one donating side, so there is no any ring formation, and due to this multidentate ligand, there is a ring formation in metal chelate. Heterocyclic ring are formed. Heterocyclic ring are formed in metal chelate. Due to this heterocyclic ring, the metal chelates are cyclic compound and they are cyclic compound. Cyclic compound or complex. Whereas metal complexes are no heterocyclic ring is forming, no heterocyclic rings forming in metal complex. They are not cyclic. They are not cyclic. In metal chelate, as we discussed earlier, that metal chelates are more stable than the metal complex. Due to in metal chelate there is a ring formation. Due to this ring formation, the entropy of the metal chelate increases. Due to that, the stability of that complexes or the metal chelate increases than the metal complexes. So here the third point is that metal chelate are more stable, whereas metal complexes moderately stable. Moderately stable. And the example of this metal chelate, if we take an example of platinum metal, the platinum is formed ring with the ethylene diamine. We know that the ethylene diamine is a bidentate ligand, can form a ring with the respective platinum complex. So due to this ring formation, the entropy of this complex is increases, and due to increase in entropy, the stability of that complex is also increases. So this effect is known as chelate effect, and in metal chelate there is a formation of ring, and this ring shows the chelate effect due to that chelating agent. Now here in metal complex there is a simple monodentate ligand, that is ammonia, formed complex with the platinum, and it have a simple structure. There is no any ring in this platinum complex. So these are the difference or the comparison between the metal chelate and metal complex. Now let's discuss what is meant by the Ian rule. So Ian rule is proposed by S.Y.B.Sc. Due to this Ian rule, we can easily calculate or the total electron count of the central metal atom with comparison with the noble gas element of that period. So let's discuss what is meant by the Ian rule. So Ian rule is nothing but that is a effective atomic number. This proposed by S.Y.B.Sc. That is a scientist according to this rule. The rule is state that the central ion or atom will accept sufficient number of electron from surrounding ligand until total number of electron associated with central ion or atom is equal to atomic number of noble gas or the inert gas element of that period. So here we take an example of that complex, that is a hexammonium cobalt complex. Or we take an example, we take an +2 oxidation state here on the complex. Now the formula, what is the formula of that ion rule? There is a simple formula for the calculation of ion rule. So let's see the formula. The ion rule is equal to atomic number of metal, that is M, minus loss of number of electron lost in Mn formation plus the number of electron gained from ligand, that is Nn. So for the calculation of ion rule, we take above the same example here. Now the atomic number of cobalt, that is 27. Number of electron lost in Mn formation, that is 2 plus, means minus 2, plus the number of electron gained by the ligand. So here 6 ammonia molecules, and each ammonia molecule means one ammonia molecule can donate 2 electrons, means that 6 ammonia molecule can donate 12 electrons. So 12. The total electron count for this complex is 37. And 37, if we write the noble gas configuration of metal, that is neon, argon, krypton, xenon and radon, then we observe that the neon have a 10 atomic number, argon has a 18, krypton is 36, xenon is 54 and radon is 86. So this electron count is doesn't matches with anyone or any noble gas element. So that's why this complex does not follow ion rule. Not follow ion rule. Now we take another example, that is a hexacarbonyl chromium complex. This is B number, it's A and B. Now again, the atomic number of chromium, that is 24. There is no any charge on the complex, means there is no any electron loss in Mn formation, because carbonyl is a neutral ligand, and so that's why there is no any charge. So here plus total number of electron gained by the ligand, that is 12, because each carbonyl can give 2 electrons, means 6 carbonyl gives 12 electrons. So the total electron count for this complex is 36, and this 36 electron can matches with this krypton. So that's why this complex can follow ion rule. So follow ion rule. So from this ion rule we can determine the stability of the complex. So let's discuss the next term, that is a labile complex and inert complex. Inert complexes are labile complex, complex. The complexes which exchange ligand, the complexes which exchange ligand rapidly that is within mixing time is known as labile complex. And the ligand inert complex is the complexes which exchange ligand, the complexes which exchange ligand at slower rate is known as inert complex, is known as inert complex. So there is a difference between the thermodynamic and kinetic stability. For example, if we take an example of these two complexes, that is hexaquoferric ion, that is and chromium complex, that is a hexaqua chromium complex. These two complexes are thermodynamically stable. Thermodynamically stable. But in kinetic point of view, the hexaqua chromium is inert, while the hexaqua ion is labile complexes. So here the chromium complex, that is hexaqua chromium, is inert, while hexaqua ferric ion is labile. The thermodynamic stability determines the inertness or the inert complexes, whereas the kinetic stability determines the lability of the complexes. So we will stop here. In next lecture, we are going to discuss how to calculate the oxidation state of center metal ion. Thank you.